Hey besties, welcome back to YellaMed. Today we're going to continue my biostatistics series and talk about two very high-yield topics commonly tested on the USMLE exams: points of prevention and study design. We'll first start with levels of prevention, primary, secondary, and tertiary, and talk about how interventions at the individual, community, and policy level can stop disease before it starts, catch it early, or reduce complications. Then we'll shift gears into study designs. This is the backbone of medical research. We'll go over descriptive, observational, and interventional studies and finish with systematic reviews and meta-analysis, which sit right at the top of the evidence pyramid. The big goal today is to help you understand not just what each prevention strategy or study design is, but how they're used in real medicine and how to recognize their strengths and limitations for exams and in practice. So let's jump in. I first want to talk about points of intervention. In other words, where in the course of disease can we step in and protect health and improve outcomes? We often think of this in three levels of prevention. First is primary prevention. This happens before disease even occurs. The goal is to stop illness from developing in the first place. Examples include vaccines, wearing sunscreen, using condoms, or public health policies like smoking bans that reduce exposure to risk factors. The next type of prevention is secondary prevention. This focuses on catching disease early when it's most treatable. This is where screening tests come in, like mammograms for breast cancer, pap smears for cervical cancer, screening for depression, or colonoscopies for colon cancer. The key idea here is that early detection saves lives. The last type of prevention is called tertiary prevention, and this happens after disease has already been diagnosed. Here, the goal is to reduce complications and improve quality of life. Examples include cardiac rehab after a heart attack, physical therapy after a stroke, or chronic disease management programs for conditions like diabetes, such as eye exams. Beyond the individual level, we also think about community-level interventions. These are policies and environmental changes that shape population health. Taxation or environmental controls are always more effective than individual education. So ultimately, it is very important to know that population interventions are always better. Some examples include taxation. This includes things like cigarette taxes or soda taxes. Another example is environmental changes, such as making sure that there's bike lanes, having smoke-free laws in public places, making sure that there's clean air or pesticide regulations. Then we have policy changes. We could have mandatory free lunch for kids, nutrition programs, or even programs requiring the schools to give children physical activity. And last is access. An example of this would be providing new access to transit to the doctor or providing access to clean water. The big takeaway here is that prevention works at multiple levels, from vaccines and screenings to policy and community design. But these strongest systems combine all three, protecting individuals while also creating healthier environments for everyone. It is extremely important to know, though, that primary prevention at the community level works better for preventing disease and unwanted health burden. All right, so let's dive into one of the most important foundations of biostatistics and research. This is study design. Knowing how a study is structured helps you judge how strong the evidence is and how much you can trust the conclusions. I first want to talk about dependent and independent variables, which are used in almost every study. An independent variable is the exposure, risk factor, or intervention being studied. An example of this would be smoking, while the dependent variable is the outcome that we are measuring that can change dependent on the independent variable. An example of this would be lung cancer. So the independent variable is the one that might cause something, and the dependent variable is the one that happens as a result. I also quickly want to touch on qualitative analysis. Not all research is about numbers. Qualitative studies focus on experiences, themes, and meanings. Methods include interviews, focus groups, and thematic analysis. These are useful in public health and health services research where the perspective of the patient matters. And now I'm going to move into different types of studies. As an overview, we're going to talk about descriptive studies that describe patterns, observational studies that find associations, interventional studies that test causality, and systematic reviews and meta-analyses that combine everything for the highest level of evidence. And as always, the details such as sampling, controls, compliance, and bias can make or break a study. So now let's get into the different types of studies I just talked about at a deeper level. So descriptive studies. These studies don't test a hypothesis, they simply describe or compare. These can either be case reports where you're talking about one patient. An example of this would be the very first case report of an HIV patient in the 1980s, or a case series which talked about multiple patients with the same risk factor or the same disease. An example of this would be clusters of vaping-associated lung injuries being tested in one case series. Descriptive studies are useful for generating hypotheses, but they cannot prove causation. Moving on to the second type of studies are observational studies. These studies explore associations between exposures and outcomes without the researcher intervening at all. The first type of observational study is called a community survey. These are just large-scale questionnaires or interviews. An example of this would just be the National Health and Nutrition Examination Survey. So they're just surveys given to the population to try to find an association between exposure and outcome. The next type of study is called a cross-sectional study. This is a study that's done for a snapshot in time. It is important to know that for these studies, we measure prevalence. I'm going to say that again. For cross-sectional studies, we measure prevalence. An example of this would be the prevalence of obesity in adults in 2003. So we see that this is measuring a snapshot in time. A limitation of the study, however, that they show association, but like all observational studies, they cannot show causation. The next type of study is called an ecological study, and this is the unit of analysis in a population and not the individual. Therefore, these studies use per capita statistics. An example of this would be comparing alcohol consumption and liver cancer rates across the countries. So a major risk factor that these studies have that I think is high yield to know is something called ecologic fallacy. This is when we assume population level findings may apply to individuals when they in fact do not. So if we find that there's super high rates of drinking in America, just because there's a high rate doesn't mean this would apply to you as an individual. The next study is a case control study. These start with the outcome and look backwards. An example of this would be looking at lung cancer patients versus healthy controls and compare smoking history. So they start with the outcome, which is people with lung cancer, and they look back to see if they have a risk factor compared to those without the disease. So these are best for rare cases, obviously, because if you have a rare case of a disease, you can look back and see if they have a specific risk factor, but it would be harder to go the other way around. It is also extremely important to know that for case control studies, we use odds ratio. Odds ratio shows the odds of developing a disease of those exposed versus non-exposed. And it's important also to know that these studies use matching to decrease confounding variables. Ultimately, case control studies establish relationship between exposure and outcome and does not establish causality. That is similar to all studies that are under observational. And the last type of observational study I want to talk about is cohort studies. These start with the exposure or the risk factor and follow patients over time and ultimately compare groups with the exposure versus without the exposure. In cohort studies, they can be either prospective or retrospective. An example of a prospective cohort study would be following smokers versus non-smokers and following them to see if they ultimately get lung cancer. And a retrospective cohort study would, for example, would say using medical records to see how asbestos exposure affected workers. So we're always starting at the exposure, whether that be smoking or having asbestos around you, and then looking to see if that caused disease or not. Cohort studies measure relative risk. This is very important to know. Cohort studies measure relative risk, and this just tells us how much did the exposure increase the risk of disease. So moving on to the next type of study is an interventional study. Here, the researcher assigns the exposure or treatment, and this is hypothesis driven. A main type of interventional study is a randomized control trial. This is the gold standard for testing causality. So interventional studies can test causality. They can say the exposure or a drug given in the trial is randomly determined, and they will see if that drug ultimately affects if people get better or get worse or whatnot. But this is hypothesis driven and it's testing causality. Did the drug test cause someone with cancer do not have cancer. So these randomized control trials use randomization. This just helps balance confounders. A lot of them are double blinded, which means the patient nor providers know what treatment is assigned, and this decreases bias. A lot of them are also placebo controlled, which just means there is one, say, pill that does nothing, and then the other one is the drug that they are trying to study. And then there's also something called a non-inferiority or equivalence trial. This just tests whether a treatment is not worse than or equivocal to the standard therapy. So an example of this is done when trying to see if a drug may be cheaper or faster than a current drug on the market. I will also put in here there are community interventions. These are just interventions done at a group level. So an example would be fluoridation of community water supplies to prevent cavities. So they are specifically giving fluoridated water to a specific community and then not to the other. And it just determines the population effect of the variable that they are giving. And I also like to step in and say that randomized controlled trials study relative risk, absolute risk reduction, and number needed to treat. Moving on to the highest level of evidence on the evidence hierarchy is systemic reviews or systematic reviews and meta-analysis. So a systematic review is a structured, comprehensive review of subjects on a topic. And then a meta-analysis pools data from multiple studies and clinical trials for a combined effect estimate. This just takes multiple randomized control trials and pools the data to try to find an ultimate overall effect. Meta-analysis are great because they have increased statistical power due to the increased number of subjects and controls. Because they are taking so much data from all different randomized control trials, they have a high N value and a high number of subjects and controls. This ultimately decreases random error and type 2 error and resolves conflicting results. Ultimately, meta-analysis are just the most precise and most reproducible because of the big population size that they are gaining through all of these randomized control trials. But I will say, even though meta-analysis are considered the highest level of evidence, they are not perfect. Two big limitations are selection bias and treatments that were given in included studies. So let me explain. Selection bias is when a researcher only includes certain types of studies. So for example, it could be only English language studies or studies with a positive result. So that starts to introduce bias. Under selection bias is publication bias, which plays into it. So if a negative or quote unquote boring study were never published, they won't be included and it skews the overall results. I will talk more about publication bias later in this podcast. The bottom line is if the selection of studies isn't representative, the pooled estimate won't reflect the true effect anyway. And then moving on to treatment differences across studies, meta-analysis pool data, but the treatments given may not be identical across studies. So for example, different doses of a drug, different durations of treatment, or slightly different patient populations can affect the meta-analysis. And this creates something called heterogeneity, which is just variation that makes it harder to directly compare results. So even if the meta-analysis says this treatment works, the practical takeaway may depend on exactly how the treatment was delivered in the original studies. So even though I just talked about some limitations, just remember that the strongest level of evidence always comes from meta-analysis, and it's because it's pooling a lot of randomized control trials. All right, so moving on, let's break down two tools that pop up a lot in evidence-based medicine, such as forest plots and funnel plots. First up, the forest plot. This is a visual summary of a meta-analysis, which is the study that I just talked about now. Think of it as a way to see what each study found and what the overall evidence says. So if you pop it up on your computer, you will see that down the middle, there is a line, and that line represents having no effect. For ratios like odds ratio or relative risks, the line is at 1. And then for differences, the plot moves either to the left or the right. So meaning the closer towards 0, such as a value of 0.1, or closer towards 10, such as a value of 9, the greater the difference. So ultimately, it's going to be a line in the middle of the graph. In order for something to be statistically significant, you do not want anything crossing that line, especially the diamond. So you want things to either be on the right or the left of the graph to be significant. Each study is shown as a box or a dot with a line through it. These represent the findings from each study included in the meta-analysis. The box equals the study's results. The size of the box equals how much weight that study carries. So a bigger study will be a bigger box. And then the line equals the confidence interval. And that shows a shorter line will be more precise, where a longer line will be less precise. And the part we really want to see is the bottom part, where you will see a diamond. At the center of the diamond, this is the pooled effect at the studies used in the meta-analysis. So if you see the top of the diamond, that is the pooled overall effect. And then the width of the diamond on both sides represents the confidence interval. So overall, when looking at these plots, if the diamond doesn't cross the line of no effect, which is 0, the overall result is statistically significant. So, okay, friends, we do not want this diamond crossing 1. A quick cheat rule is if a studies box and the line crosses the center line, that means that individual study in the meta-analysis is not significant. So each box and line represents a study. If that specific box in that study crosses the line at 1, that means it's not significant. And ultimately, if the diamond crosses the center line, the meta-analysis is overall non-significant. And then again, the bigger boxes mean stronger, more influential studies. Now the funnel plot. This tool checks for publication bias, which I talked about a little earlier. This just means we are missing studies that didn't get published. We use this plot to see if there is a bias in studies that are ultimately being published. Basically, journals are more likely to publish exciting positive findings and less likely to publish the negative ones. So we use a funnel plot to determine if all studies were published and not just the ones that showed a positive effect. If you bring up this funnel plot on your computer and look at it, on the x-axis, you'll see effect size, and on the y-axis, you will see study size or precision. Without bias, the plot looks like a triangle. That's why they call it a funnel plot, because it looks like a symmetrical upside-down funnel. In this plot, big studies cluster at the top near the true effect, while smaller studies spread out more widely at both sides on the bottom. Ultimately, if one side of the funnel is missing, this means that there are a large number of small negative studies missing, and this suggests publication bias. So we ultimately want these funnel plots to look as symmetrical as they can, and if they do not look symmetrical, if one side is missing, we know that there's publication bias, ultimately meaning that only positive results were ultimately published, and we're missing a lot of negative results. So the way to combat these publication biases is to have trial registries. These are just where researchers must log their studies ahead of time. Even if the results aren't positive, it means that they still have to publish their findings. And a cheat rule for these funnel plots, if you are a little confused, just remember symmetrical funnel equals low risk of bias, asymmetrical funnel equals possible publication bias. So moving on, now let's talk about something absolutely foundational to any study, and that's who gets included. The way participants are chosen, the study population, can really make or break the validity of the research. So first we have inclusion and exclusion criteria. These spell out exactly who qualifies for the study and who doesn't. If they're too narrow, the results may not apply broadly, and if they're too loose, the study may get a little messy and lose variability. Next, controls. Picking the right control group is critical. If your controls are not truly comparable to your cases, you're introducing bias, and that just distorts the findings. In case control studies, researchers use something called matching. This just means pairing cases and controls on certain variables like age, gender, and to make the groups more similar. This helps balance out potential confounders. And in clinical trials, we rely on something called randomization. This is randomly assigning participants to treatment or control groups. This spreads out known and unknown confounders evenly. Sometimes researchers use stratification, making sure that certain subgroups like men or women or younger versus older are evenly distributed across arms of the trial. And finally, something called concealed allocation. This is a safeguard to prevent researchers from predicting or influencing who gets which treatment. Without it, bias can creep in, even unintentionally. So concealed allocation is basically making sure that the people running the study don't have a say in who gets the placebo versus who gets the actual drug. So the big picture here is how we select and assign participants is just as important as the treatment itself. Strong sampling methods protect against bias and make the results much more trustworthy. In another one of my podcasts in this study, I'm going to talk about bias because there are so many of them, but I was just introducing it quickly here. The last thing I want to talk about is handling non-compliance in studies. No study is perfect and participants may drop out, they may fail the treatment, or get lost to follow-up. Loss of follow-up can reduce the study's validity, especially if the dropout is related to the disease or exposure. So we have some strategies we can use to handle non-compliance. One strategy is the per protocol analysis, and this is when you only include participants who followed the treatment exactly as planned. Even though this is a way that you could handle non-compliance, it is not the best way to handle. The best way to handle non-compliance is through something called intention to treat analysis. This is analysis based on the original group assignment, even if the patient didn't follow up for a protocol. So this preserves the benefit of randomization. So if a question asks you that the patient is lost to follow-up, this is ultimately something called attrition bias, and the way to mitigate this is to use intention to treat. So ultimately, even if someone drops out of a treatment plan or drops out of the study, you want to include their data, and that is the way to decrease bias the most you can. So that wraps up our episode on prevention and study design. Here's a quick recap if you fell asleep during the podcast. Primary, secondary, and tertiary prevention work at different stages of disease, but population level policies are often the most powerful for protecting health. Remember, primary population is better. Primary community level is better than individual. And then study designs build the evidence pyramid. Descriptive studies generate hypotheses. Observational studies show associations. Interventional studies test causation, and systematic reviews and meta-analysis give us the strongest level of evidence. The key takeaway is prevention tells us where to intervene, and the study design tells us how to measure whether it works. And together, they ultimately found the foundation of evidence-based medicine, which is something I live by here at YellaMed. So thanks for tuning in, besties. Don't forget to share this with your study group and check back for more high-yield breakdowns on YellaMed, especially on my next part of my Biostats series. Until next time, keep questioning, keep learning, and keep building off that USMLE knowledge. Until next time, XOXO Yella.